Before TSMC can etch a single transistor, before ASML can shine a single beam of light, before Synopsys or Cadence can compile a single line of design code, there is a piece of polished silicon 300 millimeters across that has to come out of a Japanese factory. Two companies make most of those discs. Together, they produce more than half the 12-inch silicon wafers in the world, and the entire AI economy literally sits on top of them. Most people in tech have never heard their names. NVIDIA does not make them. TSMC does not make them. The Netherlands does not make them. They are made by chemistry companies in Tokyo, in a quiet town called Imari, and almost nothing in modern electronics works without them. The two companies are Shin-Etsu Chemical and SUMCO. Shin-Etsu is a 100-year-old Japanese chemical conglomerate. Polyvinyl chloride, rare earths, silicones, pharmaceuticals, and silicon wafers, all under one corporate roof. A sprawling industrial empire. Within wafers, Shin-Etsu controls roughly 30% of the global market, the single largest share. SUMCO is the more focused of the two, formed in 1999 from a merger of two smaller wafer makers, now ranked second worldwide with around 25% share. Combined, they produce well over half the 12-inch wafers used in advanced semiconductor manufacturing. The total silicon wafer market is roughly $14 billion per year. The next three competitors, Germany's Siltronic, Taiwan's Global Wafers, and Korea's SK Siltron, together hold most of the remainder. After those five, there is essentially nobody else of meaningful scale at advanced nodes. Over the next 10 minutes, here is what we will look at. First, what Shin-Etsu actually sells, and why being inside a giant chemical company is the structural advantage. Second, how SUMCO became the specialist supplier of choice for the most demanding logic customers. Third, the part nobody outside the industry sees, how a 12-inch wafer is actually made, and why the supply chain inside that process is itself a series of duopolies. And fourth, why every attempt to catch up, including China's national effort, has failed to land at advanced nodes. Start with Shin-Etsu. The company sells far more than wafers. They are one of the world's largest producers of polyvinyl chloride, one of the largest in silicones, and a major supplier of rare earth magnets, photoresist materials, and pharmaceuticals. The Semiconductor Silicon division, branded Shin-Etsu Hondatai, is roughly 30% of the company's total revenue. But the structural advantage is not the wafer factory itself. It is the chemistry stack above and below it. Shin-Etsu makes its own polysilicon. They make their own quartz crucibles through Shin-Etsu Quartz. They supply photoresist material to ASML's customers through a separate division. They own photomask blanks. When a customer at TSMC needs a wafer with specific resistivity, specific oxygen content, or specific epitaxial layer chemistry, Shin-Etsu can adjust every input in the chain because they make every input. No other wafer producer in the world has that kind of vertical integration. Revenue is roughly $18 billion a year across the conglomerate. Operating margin sits above 30%. Capital spending is $2 to $3 billion per year, and most of it goes into expanding 12-inch capacity to keep up with AI demand. The company has been making silicon wafers since 1960 and has held the global market share lead since the early 2000s. Their customer list reads like the entire fabless and integrated device manufacturer industry: TSMC, Samsung, Intel, Micron, SK Hynix, Global Foundries, Broadcom's foundry partners. Every advanced chip on Earth contains silicon that started in a Shin-Etsu crucible. SUMCO took a different path. The name stands for Sumitomo Mitsubishi Silicon Corporation, formed in 1999 when Sumitomo's silicon business and Mitsubishi's silicon business merged. Unlike Shin-Etsu, SUMCO is a pure-play wafer maker. They do not sell chemicals. They do not sell pharmaceuticals. They sell silicon wafers and engineered substrates, period. Total revenue is roughly $3 billion a year, much smaller than Shin-Etsu in absolute terms, but operating margin is comparable, in the high 20s to low 30s%. SUMCO's strategic position is at the most advanced nodes. Their 12-inch epitaxial wafers for 5 nanometer and below logic are considered among the tightest specifications anyone produces. flatness within nanometers across an entire 300 millimeter disk, oxygen content controlled to parts per billion, surface defect density measured in particles per square centimeter. TSMC is widely understood to be SUMCO's largest customer, and the most advanced AI accelerators, NVIDIA, AMD, and Broadcom designs taped out at 3 nanometer, start on wafers that SUMCO refers to as their leading-edge epitaxial product. Capital intensity is brutal. SUMCO invests more than $1.5 billion a year in capacity expansion on top of an already massive installed base. Wafer manufacturing has a fixed cost structure similar to a power plant. The factory has to run near full utilization or the economics collapse. SUMCO has navigated 3 industry down cycles by maintaining capacity through the troughs and capturing premium pricing in the recoveries. They are smaller than Shin-Etsu, narrower in scope, and arguably more critical to the AI roadmap specifically because of where they sit on the most advanced wafers. To see why nobody catches up at 12 inches, you have to look inside the process. It starts with polysilicon, ultra-pure silicon, refined to electronic grade, sold by Wacker of Germany, Hemlock of the United States, OCI of Korea, and Tokuyama of Japan. The polysilicon goes into a quartz crucible inside a furnace that heats it past 1400 degrees Celsius. A seed crystal is dipped into the molten silicon and slowly pulled upward over many hours while being rotated. This is the Czochralski method, named after a Polish chemist who discovered it by accident in 1916. What comes out is a single cylindrical crystal of pure silicon, almost 2 meters long, with every atom aligned in the same orientation. The crystal is then cropped, ground to exact diameter, sliced by diamond wire into wafers, edge rounded, lapped flat, etched to remove damage, and polished using chemical-mechanical polishing, a slurry-based process that achieves atomic-level flatness. For advanced logic, an additional epitaxial layer of silicon is grown on top by chemical vapor deposition, providing the pristine surface where transistors will actually be built. Every single step requires a duopoly or oligopoly supplier. The quartz crucibles come from Heraeus, Toso, Shin-Etsu Quartz, or NK Group, 4 companies globally. The polishing slurry comes from Entegris, Fujimi, or Showa Denko. The wire saws come from Komatsu NTC or Toyo Advanced Tech. The diamond wire itself comes from Asahi Diamond. The epitaxial reactors come from ASM International of the Netherlands, or Applied Materials. The polishing pads come from Dow or JSR. Replicating a 12-inch wafer line is not just buying one new machine. It is qualifying every layer of a supply chain in which every layer is itself controlled by 2 or 3 companies. And here is what stops anyone new from getting in. The customer qualification cycle for a wafer at an advanced node lasts 5 to 7 years. A new supplier ships trial wafers. The customer's fab runs them through hundreds of process steps. Yield is measured against the incumbent wafer at the same conditions. If yield is even a fraction of a percent lower, the wafer is rejected, the supplier goes back and adjusts, and the cycle restarts. Once qualified, allocation starts at maybe 10% of a node's volume, growing only as confidence builds over additional years. A new entrant is looking at a decade between first capital outlay and meaningful revenue, with no guarantee of qualification at the end. Capital intensity makes the problem worse. A single 12-inch wafer line costs between $1 and $2 billion to build, and the payback window depends entirely on whether you can land an anchor customer like TSMC. China has tried the hardest. The National Silicon Industry Group, Galaxy Core Wafers, Zhonghuan, and Xing Semiconductor have spent more than a decade and tens of billions of dollars trying to close the gap. The results so far. China makes plenty of 8-inch wafers, has high market share in 200-millimeter mature nodes, and remains roughly 5 to 7% of global 12-inch wafer supply, almost entirely consumed by domestic mature node fabs. At 3 nanometer and below, the qualified supplier list outside the duopoly is essentially Siltronic, Global Wafers, and SK Siltron, 3 companies. The wafer trade is one of the most consolidated, capital-locked, and slowly moving industries in modern electronics, and the AI build-out has only tightened the squeeze. Here is the verdict. Two layers mirroring the EDA episode. Shin-Etsu first. They sit inside one of the world's largest specialty chemical conglomerates with vertical integration from polysilicon through quartz to finished wafer. The largest share at roughly 30% globally. $18 billion in total revenue, with the wafer business generating multiple billions per year at 30% operating margin. They control input chemistries that nobody else can match. They supply every advanced fab on Earth, and they are diversified enough that even a wafer down cycle does not threaten the company. Shin-Etsu is the most structurally entrenched wafer maker in the industry. SUMCO second, a pure-play wafer specialist focused on the most advanced nodes. Smaller, $3 billion in revenue, but operating margin in the high 20s, and disproportionately important to TSMC's 3 nanometer and below production. SUMCO is the supplier the AI roadmap actually rides on. Their epitaxial wafer technology is the tightest specification anyone makes, and switching away from them at advanced nodes is a multi-year requalification project no fab wants to undertake during an AI build-out. Together, they hold more than half of the global 12-inch wafer supply in a market that has no realistic challenger inside a decade. 3 risks worth tracking. 1. China's domestic wafer ecosystem. NSEG and Zhonghuan keep improving. They will be sufficient for mature node manufacturing inside China, but not for advanced AI silicon and not for export. 2. Substrate alternatives. Silicon carbide and gallium nitride substrates for power devices come from a different supplier base, and as more AI compute leans on power electronics, some of that volume goes to Wolfspeed and Coherent rather than the wafer duopoly. 3. Demand cyclicality. Wafer demand swings with global semiconductor capex, and a recession or AI capex pause hits these two harder than diversified chemical companies. The pattern is the same as every other episode in this series. 2 companies, decades of customer lock-in, and an AI cycle that pays them more, not less. This was episode 2 of Forgotten Monopolies. The companies almost nobody outside the supply chain talks about, but that decide what the industry can actually build. Next episode goes one layer further into the bill of materials, into the substrate that the chip is mounted on. 2 companies, Ibiden of Japan and AT&S of Austria, make the high-end ABF substrate that every leading-edge package depends on. The shortage that throttled NVIDIA's H100 ramp through 2024 was not silicon, and it was not packaging tools. It was substrate. If this episode taught you something nobody else is talking about, subscribe for the actual semiconductor industry view of the AI race. See you in the next one.